Okay, so thanks for having me here. This is a work that I started during my PhD outside my main project with Vlad and Neil, and it's still going on. So today I'll be talking about the small-scale structure of gravitoturbulence. If what happens or what we see the structures in the disk due to self-gravity if it is really turbulence. Going straight to the point, what is self-gravity and how it triggers the instability in the disk? That depends on this simple Q parameter. That's a balance between the shear and the thermal speed with the mass of the disk. And if you actually need to trigger self-gravitational instability in the disk, you need either a very high disk mass or you need a very stringent cooling conditions. Now, normally you have the self-gravity triggered if you have this Q value is less than some Q critical, which is theoretically 1 from the original theory of Allard-Tumbre for 2D axisymmetric disks, axisymmetric perturbations. But numerical simulations actually show a little bit of different values. For example, from Nelson et al. And Johnson and Gamy, Q critical comes out to be 1.4 from their simulations. And if you see the Crater and Lodato, this is probably the most comprehensive review on self-gravity and the gravitoturbulence and the whole self-gravity thing in the disk. There it's clearly mentioned that if you have a thickness of the disk and if you consider that, then basically the thickness of the disk stabilizes the disk more and you need a more stringent condition of Q to trigger self-gravity. So the question is, uh, we now want to, okay, we know about the role of self-gravity, either it forms planet or or it can also transfer angular momentum through spirals. But the question is, uh, if we want to trigger it, we need a massive disk. Now the question is, are the disks really massive enough? Now, from the morning, we have enough talk. Even the last one actually used a pretty massive disk that is on the onset of self-gravity instability. But the standard MMSN disk models are always gravitationally stable no matter what you do. Now, Chiang and Laughlin came up with another disk model, which is the minimum mass extrasolar nebula model. They consider the in situ planet formation, but they're like about 6 to 7 times heavier than an MMSN disk model with the same surface density. But in situ planet formation, when your migration theory is so strong at this point, I'm not sure how feasible is that, but still it is gravitationally stable. And several papers also included very low disk mass. However, there are disk masses may be heavily underestimated by assumed gas to dust ratio. Several papers have mentioned that. And recently, about a couple of weeks back, there is a paper by Powell et al., which are multi-wavelength measurement, and using the dust line, they have shown that disks may be substantially higher than MMSN. Um, Secondly, if you actually increase the mass of the disk and it becomes marginally stable, we showed initially in 2019 paper that that if you consider dust settling and dust growth, then the radiative effects can actually bring a marginally stable disk to gravitational to a state where it can be gravitationally unstable at some regions of the disk at least. And also there are emerging observational evidences that suggest that there are disks which are massive enough and can actually sustain massive enough where self-gravity can be important. So what is our motivation? So the first one is that turbulence, so it is a question posed in the review by Cater and Lodato 2016, is that we see a structure when we simulate the self-gravity, but the question is it really turbulence or is it a high M manifestation of the spiral waves? Now, if it is really turbulence, then what is the structure of the turbulence? Or is there really a way to explain or understand whether this is turbulence, or is there a simple way to do that? And second thing is how this whole phenomena affect the disk evolution and planet formation. Because if you have a self-gravity and if you have turbulence due to self-gravity, then it will have some amount of, or in some cases, pretty significant contribution to angular momentum transport. And the long-term goal is possibly coming up with a phenomenological model But apart from this, there is a bigger goal of this thing, because this turbulence modeling and the tools that you develop using this turbulence model to analyze the turbulence is actually pretty standard, and you can use this for any type of turbulence. I mean, no matter whether it comes from MRI or whether it comes from VSI. Uh, Now, we are with the alpha model for at least 40 years, and now I think we need to move from that. It's not that we need to reject alpha model, but to understand, when we assume a value of alpha, what does it exactly mean? We need to understand what the disk does in terms of its very fundamental turbulence properties. So what we do is we start with a 2D shearing sheet simulation. We just use pencil code, and we run three equations: continuity equation, momentum, and entropy. Now here you can see that FD, what's the point? Okay, so here you can see that this term here is the viscous term, the term that generates heat, and these are the terms: the hyperconductivity, hyperviscosity, and hyperdiffusivity. They actually make the solution smooth enough when a shock arises, so your simulation doesn't stop. Now, what happens is, because of this term, if you allow viscous heat to generate, your simulation box or sheet, whatever you say, that actually creates energy, generates energy, and we uh, relax that energy by a simple lambda, like a simple cooling prescription. And the cooling prescription looks like this. So it's simple beta cooling, that's what it calls. And this TC is the cooling time, which is something like beta omega inverse. Omega is the frequency, or orbital frequency. So this is our initial condition. We start with a simple sound speed equal to 3, and we start with a disk, with a shearing sheet that has the Q value slightly lower than Q equal to 1. So we initiate the self-gravity and initiate the gravitational instability there. And we also set the irradiation temperature, that is the temperature on the background, as same as the initial sound speed. So what happens is, as you are generating heat, that heat tends to relax because of this beta cooling. And the critical wavelength is 6 pi. So we actually simulate a box which is 40 times the scale height, so it contains at least 6 lambda critical for the self gravity instability. Now, here is how the system evolves. Now, on this side, here you can see the sound speed and the Q. So these two looks like same, because Q is simply proportional to the mean sound speed. But here is rho max, and here is the URMS. So you can see URMS initially increases and then goes to a statistically steady state. Of course, this is very much dependent on the cooling time that you select. Rho max, once again, initially increases, has a burst, and then it goes to a statistical steady state. Now, if you actually decrease your cooling time, what happens is it keeps on increasing and it never goes down. So that means you actually have a fragmentation. We have chosen a cooling time of 10 orbital time, so that way we make sure that we have this statistically steady state, and we have a state which we can call a gravitoturbulent state. On the right-hand side, you have the alpha hydro, also the stress that is generated hydrodynamically due to self-gravity, and the total stress. And we also show that, okay, so the total average alpha is pretty consistent with the alpha that is calculated semi-analytically by GAMI. And if you actually increase the resolution, then you converge more towards this value. So these are the snapshots of the surface density and the velocity. So basically what we do is we choose a snapshot from here where it is a statistically steady state, and then we analyze based on that. So here's the surface density. As you can see, you have shear in the vertical direction, and so you have these elongated structures both in the velocity field and in the surface density. Now, when we do the turbulence analysis, we have to move to the Fourier space first of all. So we change to the unit, which is more consistent with the turbulence unit. So we now we now select the total length of the box as 2 pi, so that we get, with the 1024 square simulation, we get the maximum wave number 512, with Nyquist wave number 256. And with this system, with this implementation, the critical wave number becomes 6.4. So here is the energy spectra. So what is it? It's actually, if you are transferring to the Fourier space, you are now calculating what is the energy content between different modes. So if you have the 2D sharing sheet, you now break it into concentric circles, and now you are calculating what is the total amount of energy lying between two concentric circles. And then you plot a logarithmic plot of k versus ek. Now, the important thing is, once you plot that, these are the reduced spectra. So before you actually calculate the energy, you so what we do is we make a summation over the other dimension. So this is the reduced spectra. As you can see, that majority of the energy is contained within in the direction which is perpendicular to the shear, and almost no energy in the direction parallel to the shear. Secondly, so what we can say is that majority of the power is in the structured flows, and there is a k to the power minus 3 variation of the spectra in the inertial range. This dotted vertical line is the k critical. So this is the largest length scale where energy is injected. And so what happens is, here energy is injected, then then the energy is dissipated at a smaller scale, and the spectra is k to the power minus third, which is consistent with Batchelor, which is incompressible 2D. But remember that our simulation is compressible, and there is a slight difference from what Batchelor 1959 got as far as the spectrum is concerned. So what happens in 2D turbulence, which is structurally and characteristically different from a 3D turbulence, is that in 3D, normally you have a larger scale or a forcing scale, and where from energy actually goes down towards the lower and lower scale, and then it gets dissipated at the Kolmogorov scale. But in 2D, you also have something called entropy, which is the square of the vorticity. And normally the cascade happens in the entropy in 2D turbulence. Now, we also saw that consistent with the structured flow, you have an anisotropy in the energy. So here we have plotted the same energy, the kinetic energy in the Fourier space. This is kx and ky. And as you can see, that you have a clear anisotropy in the direction of x. And we assume that because there is no mean field or anything that can create this anisotropy, the only reason that this anisotropy can arise is because of shear. Now, when you go to the cascade, whether this is an energy cascade or an entropy cascade, now what happens in turbulence, the most beautiful part of turbulence is that you have the nonlinear term. Now, if you have a fluid equation, whether you have the nonlinear term or not, the energy budget is the same. But what the nonlinear term does is it actually distributes energy among the scales. So this is this term which was initiated. This whole equation was given by Kreisner and Montgomery. It's a phenomenal paper published in 1980. This Tk is the energy transfer, and the other terms are the viscous energy transfer, forcing terms, and other things. But we are mostly interested about this, where you can actually write the energy and entropy flux as these two. Now, if you want a scale-independent energy flux, you need to have a k to the power minus 5/3 spectrum, whereas k to the power minus 3 spectrum is more consistent with a scale-independent entropy flux. Now, if you remember, the spectrum I showed is mostly k to the power minus third. So what we can assume is that the entropy is actually an entropy cascade, not energy cascade in a classical sense. Now, going to the structure function, this is another way of analyzing the turbulent flows, is that so you define a pth order structure function where you take the average of, this is delta Vr to the power p, is something like this. So the pth order structure function, you take a normalized pth term, pth order. So here is the third order structure function, and in turbulence theory, there are very well-established behavior of what your third order structure function should behave like. And in general, it should behave like L to the or diamond length scale to the power 3. And this is from our simulation where we got a very nice match with the simulation and the third order structure function law. This is really cool. The next one is when we plot the fourth order structure function, which is also the called the kurtosis, and we here is both these are the scale dependent kurtosis. So you keep on increasing the scale, and then you calculate the fourth order structure function here. And this one actually is a measure of intermittency, like how intermittent your structure is when you are having the self gravity into play. So in the X component, you can see that, so this is 3. 3 means you have absolutely Gaussian noise type of thing that has a kurtosis 3. But here you have somewhere, you have more than 3, so which is highly intermittent, and then less intermittent, and it has a periodic structure, which is consistent with the snapshot that I showed you, that it has, in the X direction, it has the periodic structures, but in the Y direction, it has no structure, and the intermittency is falling with the length scale. And the last one is the small scale increment. Now, this is the PDF of the small scale increment. So here is the along the Y component. So what you take is you have the velocity field in the Y direction and the velocity in the X direction. So you take an increment, and then you calculate a PDF from there. Now, what happens is we take the increment as lambda critical by 10. So this is the characteristic length scale, which is the largest length scale for the gravi-turbulence, and divided by 10. So one-tenth of that, that is the increment we have chosen. This is pretty arbitrary. So in the Y direction, we got a slight deviation from the Gaussian, but in the X direction, we have a whole structure on the left-hand side, which is highly skewed. And this is what we think is the effect of the shear. So if there are literature present who actually there are papers which actually do a lot of math and analysis to actually remove shear from the theory and make everything consistent with a non-shear turbulent flow. And we are currently using some of those to actually implement here and check whether this structure is really consistent with the shear or not. So this is an ongoing project, and this is what we are doing now. We want to understand the large scale, the effect of the large scale shear. What is the and we want to put the gravi-turbulence in the framework of the general turbulence theory. Like uh, from the results I showed, it's now pretty clear that to some extent the gravi-turbulence actually behaves like a turbulence from the spectra and other properties. We want to come up with a very comprehensive model of the small scale dissipation. Like if you have energy injected in the higher scale, how much energy is deposited in the lower scale, and how it is contributing to the heating of the disk, and what is the numerical dissipation, and what is its effect, because pencil is numerically a bit dissipative, so probably going to a more spectral framework, and the interplay of the radiative time scale, because when you are running these things, you have a turbulence time scale which is nonlinear, general nonlinear time scale. At the same time, you have a cooling time scale, how these two affect each other. And so that's where I will end, and I will take questions if there is any time.
Questions, but can you put up your equations again, because I was so you had in the entropy equation you had a term that involved a viscosity.
That's right.
So is that, but you also have a viscosity in the momentum equation, and that is not hyperviscosity, or is it? Which one is hyper and which isn't?
Hyperviscosity is F nu, this one.
So, and the viscosity that's in the entropy equation, that's hyperviscosity as well.
Oh no, this one is the term that is creating the heating because of the viscous effects and the shocks.
So, but there are both viscous effects and shocks.
I think these are mostly shocks. The heat generated due to shocks, and this is the heat that is dissipated due to cooling. So that's
And
how
what
the
is F?
balance.
What is the right-hand side then? The
Oh, this
rightmost.
one is the hyperconductivity. Yeah.
Sorry, I was also slightly confused by this. Are you running in pencil code what's called a shock viscosity there, or what we'd otherwise call a von Neumann type viscosity?
I think so. Is that, yeah.
Okay, so there's a von Neumann shock capturing viscosity term and hyperdissipation, which is actually what I'd expect for pencil to keep the problem stable. So there must also right. So that's the heating there. So there's a pressure contribution effectively in the momentum equation from the shock viscosity somewhere too.
Yeah, we actually expect some amount of compressible work done and effect on turbulence as well, like what kind of
Well,
heating.
so I think you might be missing something in how you've typed down the momentum equation for the shock viscosity. That's what might be causing the confusion here. There's a matching term there for the heat that's deposited into the entropy. That's yeah. But I think that I think that's what's going on, because I was confused when you didn't say shock viscosity.
Okay,
When
I
we
will
talked
look
about
into
this.
the equations
Yeah, okay.
again,
Yeah.
exactly what I ran.
Said that it looks different from normal turbulence, because it seemed like most of the results you showed look.
No, I didn't say
similar.
is the different from the normal turbulence. I said it. Okay, so the shear actually makes a difference, right?
Is that just on the large scales though, or because
It's
it looked
from the
like
large scale
it only
shear.
went down to the large scales where the shear was important, right?
Yeah, the large scale shear. Now what we are working on right now is that to remove the effect of shear and to put it in a framework of a turbulence theory where there is no shear, because Cassiola et al. They did exactly this kind of things, and then you can match things much more prominently with what the conventional turbulence theories are.
If you just look at at much smaller scales, though, wouldn't you find something similar?
In the smaller scale, they are acting pretty similar to the normal turbulence, uh, but a conventional, not a 3D one, but a conventional 2D one. That much we are sure. So that is why we are more prone to say that, okay, this is not a high M manifestation, it's actually a turbulent structure. But the large scale shear, we need still need more work to do.
This one. So I guess you convince us that the turbulence itself is not isotropic. Yes.
Sorry.
You convince us that the turbulence itself is not isotropic. You show us a contour plots in X and Y, and this is
Yeah, we think that it's not isotropic, and it's happening because of it's that isotropic shear driven.
Yeah, I understand that. So, but then when you actually write down equations, there's just one K. Are you still averaging over a K space to write down equations? And why would you do
No,
that?
we are not. We are not. I mean, I haven't shown any equation in the K space.
I saw that you have written expressions for the turbulent energy as an integral over K of certain things.
Oh, okay,
Why
okay.
is it,
So you are talking about
that one, for example.
this one?
Yes.
Yeah. So
What
it's
K is
actually
that?
so it's actually reduced spectra. So it's Kx and Ky basically.
That K there is Kx and Ky.
Yeah. So you can say this K to the power minus 3 is actually so reduced spectra. So we are basically summing over the direction parallel to the shear. So it's actually the K in the direction perpendicular to the shear.